All right, let's jump right in. Today, we're going to tackle something super fundamental in digital logic. We're talking about how to take a straight-up linear three-variable truth table and transform it into its much more powerful cousin, the Karnaugh Map. And don't worry, we're going to build this thing out step by step so you'll see exactly how it all comes together. So here's the mission, right? On one side, we've got our starting point, an empty grid, and all the data from our truth table. And on the other, that's our destination, the fully completed map. Now, the goal here isn't just, to copy-paste data. No way. We're actually transforming it into a visual tool, one that lets us spot patterns you'd never see otherwise. So let's break down exactly how we get from A to B. This graphic displays a standard linear three-variable truth table on the left and an empty two-dimensional Karnaugh map, or K-Map, on the right. Our objective is translating data from that truth table into the K-Map's spatial grid. Looking at the K-Map structure, the columns represent the states of the higher bits, variables A and B. The rows represent the state of the third variable, C. We construct this spatial grid to simplify complex Boolean algebra expressions. This grid displays the exact binary input combinations inside each cell. The columns dictate the first two digits, and the rows dictate the third. For example, the top left cell intersects at A equals 0, B equals 0, and C equals 0, giving us the combination 0, 0, 0. To make plotting faster, we use minterm numbers. A minterm is a specific logical codec of all the variables in a function, corresponding to exactly one row in the truth table. These yellow digits, 0 through 7, act as a visual shorthand that directly links the binary truth table rows to specific spatial coordinates on the K-map. Understanding this structural layout and shorthand is the mandatory foundation. We have to know exactly where each row belongs before any actual data can be transferred from the truth table to the map. We begin the mapping process by locating the first truth table row, where all variables are 0, A', B', C'. This corresponds to minterm 0. An input of 0, 0, 0 produces an output of 1, mapped directly into the top left cell. Next, we move sequentially to the second row, A', B', C', representing minterm 1. Changing only variable C to 1 pushes the mapped output directly below the previous cell, placing our next one into the bottom left coordinate. Keeping A and B constant while flipping C moves the data vertically within the same column. We advance to the second column by changing variable B to 1. This addresses the A', B, C' row, or minterm 2. The truth table shows an output of 0, which maps into the second cell of the top row. We then map the next sequential row, minterm 3, where A is 0, B is 1, and C is 1, to the cell directly beneath minterm 2. This mapping confirms a steady left-to-right progression. However, that pattern is about to be intentionally broken. The most common mistake during K-map plotting occurs right here, incorrectly mapping the transition from minterm 3 to minterm 4 into the adjacent third column. The top headers strictly follow a gray code sequence, where successive values differ in only one bit. Because of this, the combination of A equals 1 and B equals 0 bypasses the third column, landing in the upper right corner cell. Following the established vertical rule, we map minterm 5, where A equals 1, B equals 0, and C equals 1, directly below minterm 4. Respecting this gray code jump is the single most critical step. Failing to skip the third column causes all future simplifications to fail. Now we return to the skipped third column to map the final remaining combinations, where both A equals 1 and B equals 1. We map minterm 6, corresponding to A equals 1, B equals 1, and C equals 0, to its rightful place in the upper third column cell. While logically sequential in our table, it visually fills the inside of the map. We place the final row, minterm 7, directly beneath minterm 6 in the lower third column. Mapping out of sequence visually guarantees that adjacent cells only ever differ by a single variable, which is the entire structural purpose of the gray code architecture. This graphic shows the fully populated three-variable K-map in its final state. Every single linear row from the truth table has been successfully translated to an exact, verifiable spatial coordinate on the grid. This perfectly mapped two-dimensional grid is now mathematically sound and fully primed for the final phase,
grouping adjacent ones for Boolean algebra simplification.
This is a three-variable Karnaugh map, a geometric grid that organizes logical states to reveal redundancies. We start with the uniting theorem, looking specifically at this vertical pair of adjacent ones highlighted in neon green. The core mechanic is simple. Grouping adjacent ones eliminates the specific variable that changes state within that group. Moving from the top cell to the bottom cell, the variable z flips from a 0 to a 1. Because it changes, it's completely irrelevant to the outcome. It vanishes, leaving us with just x prime times y prime. This rule applies regardless of direction. Look at this new configuration, focusing on the purple horizontal pair in the top right. Scanning across this horizontal group, the y variable changes state, crossing the boundary from y into y prime. The variation cancels it out, leaving behind a simplified expression of x times z prime. This establishes our baseline rule. Visually looping a pair of adjacent ones automatically destroys one redundant variable from your circuit. But the geometry scales up in powers of 2. You aren't limited to grouping in pairs. Capturing 4, 8, or even 16 adjacent ones simultaneously strips away logic even faster. This visual highlights a massive group of 4 ones taking up the left half of the map. Because a quad spans 4 distinct cells, 2 variables change state. Tracing the edges, y and z flip across this area. Both are eliminated, leaving only x prime. This pattern recognition holds steady anywhere on the grid. Here is a block of 4 perfectly centered in orange. Checking boundaries, x flips across the top columns, and z flips along the side rows. Y doesn't change state. The quad simplifies to a single letter. The grouping can also stretch out. This diagram shows a continuous light blue row of 4 along the bottom. Traveling horizontally across this span, x and y are constantly shifting from column to column. Z is the only variable anchored in place. Maximizing the physical size of your glowing shapes directly correlates to minimizing your logic. The larger the geometric block you capture, the less hardware you have to physically build. There is a spatial twist to how these maps work. The grid is not a flat, isolated plane. It acts as a continuous surface where opposite edges wrap around and touch. Look at these 2 red groupings on the far left and right columns. By wrapping the edges together, they merge into a valid group of 4. They share those outer borders, where the y prime state remains constant. This cleanly simplifies down to y prime. You have to look past the drawn borders. Viewing the map as a continuous cylinder exposes hidden efficiencies. Let's sprint through a live application. We start by taking a raw truth table, a simple mathematical list mapping all possible inputs to their desired outputs, and plugging it into a blank map. This visual maps our truth table outputs directly onto the grid. We execute our first strategic move by capturing the largest obvious group, this orange vertical pair on the left column, which simplifies down to a prime times b prime. Next, we capture it by pairing it horizontally with its neighbor, giving us a blue loop that simplifies to a prime times c. Finally, we grab the last isolated one on the bottom right. Pairing it horizontally creates a green loop, isolating the variables b and c. Every active state, the complete onset from our initial truth table, is now fully covered by distinct geometric shapes. Stitching those 3 distinct groups together gives us a simplified Boolean expression, but the puzzle isn't actually finished yet. Look closely at the completed board. One of our shapes is unnecessary. The blue horizontal group perfectly overlaps the orange and green ones. Because every one inside that blue shape is already covered, the a prime c term is redundant. We can delete it. Arriving at that exact deletion through pure algebra requires multiple tedious steps of factoring. Here, the redundancy is visually exposed the second we draw the loops. These visual laws are highly resilient. This diagram shows alternative layouts, proving that whether the board is drawn vertically or with a different variable order, the geometry dictates the same mathematical truth. Karnaugh maps turn heavy, error-prone algebra into instant pattern recognition. By translating logic into physical space, you easily strip out redundant variables, saving hardware, time, and valuable processing power.
Thanks for watching. See you next time.